Parallel programming is hard. The barrier to entry is far too high. We live in a world where almost all hardware platforms are parallel and require explicit programming to use that parallelism. Despite that, many users and many code bases do not take advantage of the available hardware parallelism. For those that do, many have chosen approaches that are platform-specific and not portable. For example, most code that is written to take full advantage of the many cores on a powerful CPU can't run effectively on a GPU. So the C++ committee wants to build an on-ramp to parallel programming. We want to give users easy-to-adopt solutions that are widely portable. We're not aiming to expose all the capabilities of each platform, but instead to expose enough of each platform's parallelism to be useful. We want widespread adoption and normalization of parallelism across the C++ ecosystem. There's 3 pillars to our strategy for parallelism in standard C++. First, we need a corpus of common algorithms that dispatch to vendor-optimized parallel libraries. Next, we need tools to write your own generic parallel algorithms that can run anywhere. Finally, we need mechanisms for composing parallel invocations into task graphs. Today, I'm going to talk about the C++ Standards Committee's plans for bringing parallelism, asynchrony, and accelerated computing into standard C++, about how the committee is supporting all 3 of these pillars. I am David Olsen, lead engineer for the NVIDIA HPC C++ compiler, NVC++, and member of the C++ Standards Committee. My job for the last few years, and likely for several years to come, has been to implement C++ standard parallelism for both CPUs and NVIDIA GPUs within the NVC++ compiler. I would be remiss if I failed to thank Bryce Adelstein-Lelbach, who originally put this presentation together. I have modified it and updated it to be my own, but all of the best parts came from Bryce, and all of the inaccuracies are mine. There will be lots of code examples in these slides, and I will go through them quickly. I don't expect you to understand all the code. Instead, focus on the high-level takeaways, which I will attempt to highlight and repeat. Because this is slideware, I have used some namespace aliases for ranges, views, and execution in this thread to save space on the slides. With those caveats out of the way, let's move to the main content. We'll start by talking about the first pillar, the collection of common parallel algorithms. C++ has had a set of serial algorithms for manipulating sequences of objects since the first standard. These algorithms operate on one-dimensional sequences. Initially, they were parameterized with iterators. But with C++20, we've introduced a new, more powerful abstraction, ranges. There's about 100 different standard C++ algorithms for loop abstractions, filters, sorts, searches, rotations, reductions, scans, etc. In C++17, we introduced parallel versions of these algorithms. The parallel overloads have the same interface as their serial counterparts, except they take an extra parameter, an execution policy, which describes what form of parallelism is allowed, if any. Execution policies describe the how of execution, but they don't specify where. That's left up to the implementation. Execution policy parallelism could be implemented with a variety of strategies, such as a CPU thread pool, OpenMP, or GPU acceleration. Execution policies permit parallelism, but do not require it. An implementation may choose to not parallelize. The execution policy overloads are all fork-join synchronous, or blocking. The implementation will wait for the parallel operations to complete before returning from one of these algorithms. There are 4 execution policies. Seek, short for sequential, indicates that all operations must be performed within the calling thread and must be indeterminately sequenced. Basically, it says no parallelism is allowed. Unseek also requires all operations to be performed in the calling thread, but allows those operations to be unsequenced or interspersed with each other, meaning that vectorization is allowed but not required. Par allows the implementation to parallelize operations at its discretion. However, it also requires that all operations within each thread be indeterminately sequenced, meaning that vectorization is not allowed. Par unseq allows operations to occur in multiple threads and to be unsequenced with respect to each other, meaning that both thread and vector parallelism is permitted. Again, this means parallelism is allowed, not required. The implementation may choose not to parallelize. Let me show you one of Bryce's favorite parallel algorithm examples, word count. We can write it in a single parallel transform reduce. Transform reduce takes both a transformation operation and a reduction operation. It applies the transformation to the inputs and then uses the reduction to sum the results of those transformations. If you're familiar with MapReduce, this is C++'s form of it. We'll use the overload of transform reduce that takes two input sequences and a binary transformation function. The first input sequence will be the entire string except for the last element. The second input sequence will be the entire string except for the first element. This means our binary transform function will be passed a window of every two adjacent characters in the string. Our transformation function's job is to tell us whether the two adjacent characters it's looking at are the beginning of a word. If the left character is white space and the right character is not white space, then the right character is the beginning of a word. The pseudo-sequence produced by the transformation will look like this. For every word, one and only one of the transformation invocations returns true. But what about the first character of the string? We never actually test it with our transformation function. We start at the second character. So we account for the first character in the initial value of the reduction. Our reduction operator is just plus. After the transformation, we have a sequence of bools. Summing that sequence into an integer will give us the word count. This standard C++ code is parallel and portable. You can run it anywhere, on your GPU, your server CPU, your laptop, even your phone. In C++20, the standard library introduced ranges. Unlike iterators, ranges are composable. Ranges allow us to express a wide variety of algorithms in terms of a few key primitives. Used in conjunction, C++20 ranges and the C++17 parallel algorithms are quite powerful. Standard C++ algorithms iterate over a sequence of objects, for example, the elements of a container. However, sometimes we want to iterate through indices instead of objects. This is particularly important in numerical and scientific computing. We can do that using iota, a range factory introduced in C++20. It produces a range of monotonically increasing integers. For example, iota 1, n will produce a range of all integers from 1 to n-1. Instead of passing iterators to a container to a parallel for each, we can instead pass an iota range, giving us a parallel for over indices instead of objects. We can also use parallel algorithms and ranges to iterate multidimensional index spaces. C++23's Cartesian product range adapter takes multiple input ranges and produces a range of all the ordered tuples formed by taking an element from each input. It essentially reduces a multidimensional index into a one-dimensional index. We can use this in conjunction with iota to create ranges representing multidimensional index spaces. For example, here we use this pattern to write a simple parallel matrix transpose. The range V will produce two-element tuples from 0, 0 to n-1, m-1. The iteration order will be row major. The second index will be contiguous. We can change to column major by switching the order of arguments to Cartesian product. The C++17 execution policy parallel algorithms are fork-joined synchronous, so each invocation launches its work in isolation and blocks until that work completes. So for example, if we invoke two parallel for eaches on the same data back-to-back, we'll get two parallel work launches. The caller will be blocked, waiting for the first invocation to finish. Only then will the second invocation be enqueued and launched. This transfer of control back to the caller is a latency bubble and can degrade performance. One way to address this problem is to fuse the operations together into a single parallel invocation, which can be done with the transform range adapter. Transform takes an input range in a function and returns a range that is the result of applying the function to the input. This is completely lazy. The function is only executed as needed when the elements of the returned range are accessed. For example here, f is not evaluated until the elements of v are accessed in the parallel for each. There's a big change in semantics here. Previously, we had a guarantee that all invocations of f would happen before any invocations of g. We no longer have such a barrier. Another useful range adapter is filter, which takes an input range and a predicate function and produces a range of all elements of the input for which the predicate returned true. Again, this is done lazily. The predicate isn't evaluated until the elements of the returned range are accessed. Here, we use filter in combination with a parallel reduction to sum only the positive elements of a container. Let me show you some applications that have adopted standard C++ parallelism. LULESH is a mini-app for Lagrangian explicit hydrodynamics on an unstructured grid. It's designed to stress vectorization, parallel overhead, and on-node parallelism. It's been ported to several frameworks and programming models, including MPI, OpenMP, OpenACC, CUDA, Raja, Cocos, and now standard C++. With the standard C++ version of LULESH, you can get performance that matches many of the other backends, and you can build that same standard C++ code with multiple compilers, GCC, NVC++, Intel, MSVC, and run it in parallel on either CPUs or GPUs. Another example is STLBM, a lattice-Boltzmann framework written from the ground up in standard C++. It can run on multi-core CPUs and GPUs without any code changes. It doesn't use any language extensions, external libraries, vendor-specific code annotations, or pre-compilation steps, just standard C++. Maya, a code base for aerospace and noise simulations, has ported to C++ standard parallelism. They're planning to move from OpenMP to standard C++. The C++ parallel algorithms introduced in C++17 are great, but they're just the start of the story. They have two major limitations. First, the C++17 parallel algorithms are all fork-join synchronous. They launch the parallel work, and then they wait until that work is completed before they return to the caller. Now, where exactly do they launch that parallel work? That's the second problem. By design, users have no control or visibility into where the parallel work runs. It happens on some amorphous implementation-defined execution context. It could be a CPU thread pool, a GPU stream, Grand Central Dispatch, Windows fibers, etc. Implementations have complete freedom. Today, C++ has no standard model for asynchrony and no standard way to express where things should execute. But the solution is coming soon to your C++ implementation, senders and receivers, an asynchronous execution framework for standard C++. Let's look at a simple example. First, we need to get a scheduler from somewhere, from a thread pool, a tasking system, a GPU driver, etc. To start a chain of work on the scheduler, we call schedule, which returns a sender. That sender will complete on the execution context associated with the scheduler. Next, we use a sender algorithm, then, to compose work onto the sender that we got from the scheduler. This work will be performed on that same execution context. The sender algorithm will return a new sender, which we can use to add more work onto the chain. Finally, we wait until the chain of work is completed using sync wait, which will return the value sent by the final sender in the chain. There are three concepts in the model: schedulers, senders, and receivers. Schedulers are handles to execution contexts. Schedulers produce senders. Senders represent asynchronous work that will eventually send a signal. They can be composed together with sender algorithms to form task graphs. Receivers process asynchronous signals from senders. Let's look at schedulers in more detail. I said they are handles to execution context, but what exactly does that mean? An execution context is a resource that represents the place where execution will happen. This could be a concrete resource, like a specific CPU thread pool or a GPU stream. It could be a more abstract resource, like the current thread of execution. Execution contexts don't necessarily have a representation in code, and today they don't have any exposed interface. They may have state associated with them, OS handles, memory, metadata, etc. Schedulers represent a strategy for submitting work to execution contexts. They are lightweight, non-owning handles to contexts. Schedulers are cheap to construct and pass around. Execution contexts hold all of the state. Multiple schedulers may refer to the same execution context, including multiple different kinds of schedulers. For example, you might have two schedulers that submit work with a different priority. You might even have a scheduler that dispatches work to multiple different execution contexts. We use schedulers to produce senders that will perform work on the execution context associated with the scheduler. Once we've obtained a sender from a scheduler, we can compose work on it. Now, let's look at senders and how we actually compose them. As I said before, senders represent asynchronous work. They form the nodes of an asynchronous task graph, which may span multiple schedulers and multiple execution contexts. Senders are lazy. You must explicitly start them. When a sender's work completes, it sends a signal to the receivers attached to it. Receivers are handles that get notified with a signal by the sender. There are three different handling paths, which are called channels. The value channel is used to indicate successful completion and may pass one or more values to the receiver. The error channel indicates that the sender's work failed and passes an error object that contains information about the failure. The done channel is used to indicate that the sender's work was canceled before it could be performed. This is distinct from the error channel because cancellation is not an error. It may happen during the course of normal operations. Each sender notifies its attached receivers with one signal, meaning only one of the three channels is invoked. Now let's look at how senders and receivers are hooked up to each other. Let's start with some scheduler, which we will get a sender from. A receiver is attached to a sender via connect. That's a behind-the-scenes interface that won't usually appear when using asynchronous operations. Connect returns an operation state, which contains the actual work that the sender represents. Eventually, you initialize the work by calling start on the operation state. After some time, the operation completes and then notifies the receiver with the signal. One important note before we move on to the next topic. It is unlikely you will ever deal with receivers or operation states or the connect and start functions. The public API for senders and receivers is schedulers and senders, not receivers. The algorithms that I will talk about shortly take and return senders. Unless you are writing your own senders algorithms, you won't need to write any receivers. Next, let's look at sender composition. We compose together senders using sender algorithms, of which there are a few forms. The first is sender adapters. Sender adapters take one or more senders as parameters and return a sender. Most sender adapters are pipeable, just like range adapters. The semantics are similar to Unix shells. Send pipe f pipe g is equivalent to g of f of send. Languages like Haskell and APL call this point-free style. The primary input argument is not explicitly named. This syntax is essential for elegant composition of senders. Composing senders via nested function calls is a mess. The order in which operations occur is inverted from the order in which they appear in the code. The predecessor senders are more deeply nested and thus appear after their ancestors. Things get a bit cleaner when we instead use a temporary variable for each step of the composition. However, this is error-prone. it's easy to mix up one of those named variables. The pipe syntax gives us a clean way to compose chains of senders in the order that they will be evaluated. Now, let's show you some of the most important sender adapters. Then takes an invocable, f, which calls it with the values sent by the prior sender. The sender returned from then will send the results of the invocation of f. This is how you attach a continuation to a sender. Bulk is the parallel version of then. It evaluates the invocable once for each index in the shape n. In the simplest and most common case, the indices are one-dimensional and start at 0, and the shape argument is an integer indicating how many invocations to perform. The sender returned from bulk will pass along the signal from the prior sender. Transfer changes the scheduler that will be used for the next sender. It doesn't change the scheduler for the prior sender, only the subsequent ones. Some senders can only be connected to a single receiver, for example, because they move any values or errors they send instead of copying them. We call these one-shot senders. Senders that can be connected multiple times are called multi-shot senders. Split takes any type of sender and returns a multi-shot sender that passes along the signal from the original sender. Split senders represent forks in sender task graphs. Conversely, when all takes multiple input senders and returns a single aggregate sender that will combine the signals from all the input senders. Senders returned by when all do not have a scheduler associated with them, which means they do not promise when they complete, where they complete. When all senders represent joins in a sender task graph. When all is not a pipeable sender adapter, as the partially applied piped form would be ambiguous with the fully applied non-piped form. Ensure started connects and starts a sender, returning a new sender that will pass the signal sent by the original. If the input sender is a composition containing other senders, those senders will be connected and started as well. Senders are lazy by default. They won't run until their result is needed. Ensure started is used to turn a lazy sender into an eager sender, where the work starts right away and happens concurrently in the background. Sender factories are another kind of sender algorithm. They don't take senders as parameters, but they do return a sender. Sender factories are used to start new chains and graphs. The senders they return are the root nodes. We've already seen one sender factory, schedule, which returns a sender that completes on the specified scheduler. The return sender doesn't send values or represent any actual work. It's just a handle you can use to compose work on the scheduler. Just is another sender factory. It takes a set of values and produces a sender that will send those values immediately when connected. This is how values are inserted into a chain of senders. The last kind of sender algorithms are sender consumers. They take senders, but they do not return senders. They typically launch a sender graph by connecting and starting it. They are the leaf nodes of sender graphs. Sync_wait is a sender consumer and synchronization primitive that blocks until a sender completes and then returns or throws whatever was sent. Now let's discuss the details of how sender graphs get formed. Suppose we have a single link in a chain of senders. We have an abstract before sender adapter on the left side of this link, a concrete then adapter, and an abstract after adapter on the right-hand side. If we unroll the pipe syntax, we'll have something like this. We've got a before sender that came from somewhere. We create a then sender, which will contain the before sender and the function f. We'll also create an after sender, which will contain the then sender. We'll end up with a nested structure of senders. At some point, we'll connect a receiver to the outermost and last sender. Each sender in the nested structure will connect a receiver to its child. This happens in the opposite order of sender construction. That will give us a nested receiver structure that's the inverse of the sender structure. A nested operation state structure is also produced and returned from connect. Eventually, we'll start that operation state. As the operations complete, they'll begin notifying their receivers with signals. When the before receiver gets a signal, it will notify the then receiver. If it's a value signal, the then receiver will invoke f with the value and signal the after receiver with the result of that invocation. Let's look at a more advanced example, a generic asynchronous and parallel inclusive scan. We'll write it as a pipeable sender adapter so that it can be composed with other sender algorithms. Sender adapter here is some wrapper type that turns a lambda into a sender adapter object. It'll take 3 parameters, a sender, which we'll expect to send the input as a range, an initial value, and the number of tiles to split the input into. We're going to use the classic 2-pass parallel scan approach, which requires a temporary storage for partial results communicated between tiles. We need to allocate this temporary storage asynchronously once the prior sender has sent us the input. So we'll chain a then sender onto the prior sender. In the body of the continuation, we'll create a vector to hold the partial results. We'll return both the input range and the vector. Next, we'll need to do the first parallel pass, the down sweep. We'll use bulk to invoke the body of the pass for each of the tiles. The first thing we do for each tile is calculate the range of elements that belong to the tile. Then we take all of the elements in each tile and perform a local serial inclusive scan on them, which we do right here. Next, we need to propagate information between the tiles. The sum of each tile needs to be added to the elements of all preceding tiles. We've already computed that sum. It's the last element of the local inclusive scan. We store that result in the partials vector. Assignments to the partials from different tiles may happen concurrently, but that's fine. Each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data race here. Then, after all tiles have completed their local inclusive scans and written to partials, we need to have one execution agent do a serial inclusive scan of partials. We do this by piping another then sender onto the chain, which will perform the partials inclusive scan. This then sender will again pass along the input sequence in the partials vector. Can you lower the blinds? The information that each tile needs to add to its element in the partials slot for the tile directly preceding it. The information that each tile needs to add to its elements is the partial slot for the tile directly preceding it. Now we need to go parallel again to distribute that information within all tiles. This is the upsweep pass. So we'll pipe another bulk, once again over all tiles. In the body of this bulk, Can you lower that one? In the body of this bulk, we'll need to calculate which elements belong to the current tile, just as we did before in the downsweep pass. Then we use a serial for each to increment each element in the tile by the appropriate value from the partials vector. After that addition, we'll have the correct result. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector. So we had a final then sender which only passes along the input. The partials vector will be destroyed when this then sender completes. And that's it. We're done. Whew. This is too much code and too small of a font, covered much too quickly for you to read and understand it right now. But I do want to pause here for a few seconds to point out some important takeaways. We have used several sender algorithms, some of them parallel algorithms, passing values from one sender algorithm to the next, using the convenient pipe syntax. The result is a generic asynchronous parallel inclusive scan. It is a task graph that describes the work to be done. We can arrange for the work to run whenever we want, to any scheduler that we want. Or we could combine this task graph with other senders so it is part of an even bigger task graph. We've developed a prototype implementation of standard C++ senders and receivers that supports CPU schedulers, GPU schedulers, and distributed schedulers. Let me show you some examples and applications that we've already ported to senders and receivers. This simple electromagnetic wave simulation solves Maxwell equations on a uniform grid. This is the entire solver loop, which is expressed as a graph of senders. This code can be run with a variety of different schedulers. By changing just one line of code, the kind of scheduler passed to the solver, we can go from running in line on a single CPU thread to running in parallel on the CPU using OpenMP, to a single GPU, to multiple GPUs within a single node, and to multiple nodes scaling up to thousands of GPUs. With standard C++ senders and receivers, you can change one line of code and scale from a single CPU thread up to an entire cluster of GPUs. Polybos is a framework for parallel computational fluid dynamics simulations using the lattice-Boltzmann method. We've ported one of its applications to standard C++ senders and receivers. This simulation models carbon sequestration techniques. The porous structure you see is sandstone. It is filled with saturated salt water, which is not visible in the representation. The red bubbles correspond to liquid carbon dioxide, which is injected at the bottom and travels through the sandstone because of buoyancy forces. Using our distributed GPU scheduler, we're able to run this application at scale on up to 512 GPUs. Senders and receivers are the next major step in the deployment of C++ standard parallelism. They deliver the second and third pillars of our plan. The framework gives us the tools we need to write our own generic parallel algorithms that can run anywhere and to compose asynchronous task graphs. Today, C++ has no reasonable abstraction for multidimensional data. This is unfortunate, as many of the interesting compute-heavy problems that benefit from parallelism have a multidimensional shape. That's why we're introducing Mdspan, a multidimensional span type in C++ 23. It's very similar to the one-dimensional span introduced in C++ 20. Mdspan is non-owning. It's just a handle to some underlying data. It doesn't manage the lifetime of that data. Mdspan is cheap to copy. It just contains a pointer and metadata describing the size and shape of the structure. Metadata such as the extent of a dimension can be expressed either at runtime or compile time, allowing for metaprogramming and compile time optimizations. Mdspan parameterizes how a multidimensional index is mapped to a location in the underlying data. We call this parameter a layout, and it can express any kind of multidimensional structure. There are some concrete layouts in the standard library for common use cases, but anyone can define their own layout and plug it into an Mdspan. Likewise, Mdspan parameterizes how it accesses the underlying data. The default is to just perform a normal C++ pointer dereference with an index. With a custom accessor, you could instead use a special cache bypassing instruction, read from disk, or perform a remote memory access. Mdspan uses extents objects to express the number of dimensions in a space, the rank, and their length, the extents. Extents objects take a size type and a variadic number of integrals of that type as template parameters. For dynamically sized extents, the magic value dynamic extent is used as an integral template parameter, and the extent is passed to the constructor of Mdspan, Through the power of C++ 20's class template argument deduction, when you're working with all dynamic extents, you usually don't need to spell out the entire verbose instantiation. There's also an alias dextents for the all dynamic extents case. It takes a single parameter, an integral specifying the rank. For statically sized extents, the extent itself is passed to an integral template argument. No corresponding constructor argument is needed. You can mix static and dynamic extents. For example, in this case, we have one static extent and one dynamic extent, so we'll need to pass just one extent at runtime. Extents objects in Mdspan support arbitrary rank. You can have as many dimensions as you want. Mdspan has 4 template parameters, 2 of which are optional. The first is the element type. The second is the extents type. This must be a specialization of the extents class template. The third is layout. The default is layout right. We'll discuss layouts more in a few moments. The final parameter is an accessor, which performs element access. Mdspans of all dynamic extents have a simple syntax. With class template argument deduction, you can construct one without specifying any template parameters. If you do need to spell the type out, it's still concise. Just use the dextents alias. The elements of an Mdspan are accessed via the index operator. Thanks to a recent core language change in C++ 23, indexing operations can now take multiple parameters. You can also make Mdspans of static or mixed extents. The simplest way to construct these is by passing an extents object as the second constructor argument. Now let's talk a bit more about layouts. The 2 most common layouts are layout right and layout left. With layout right, the rightmost extent is contiguous, meaning its stride is 1, and strides increase right to left as the product of extents. This is the layout for C++ built-in arrays and NumPy. It's also the default for Mdspan. For example, if we had a 2x2 matrix, the 2 elements on the first row would have data locations 0 and 1, and the elements on the second row would have data locations 2 and 3. With layout left, the leftmost extent is contiguous. Its stride is 1, and strides increase left to right as the product of extents. This is the layout used by Fortran arrays and by MATLAB. If we had a 2x2 matrix in layout left, the 2 elements in the first column would have data locations 0 and 1, and the 2 elements in the second column would have data locations 2 and 3. There's also a standard layout that allows you to explicitly specify the strides for each element. All 3 of the concrete layouts in the standard library are just implementations of the layout concept. Generically, a layout is just something that maps a multidimensional index to a data location. Anyone can define a layout. Layouts may be non-contiguous. They may map multiple indices to the same location. They may perform complicated or expensive computations. They may have or refer to state. Parameterizing layout is critical because it allows us to write generic multidimensional algorithms that can be used with any layout. This is an essential component of portability because different layouts may be needed on different platforms to deliver on performance. Today, we have a major vocabulary problem with multidimensional types in the C++ ecosystem. Suppose I write a function that uses a concrete owning multidimensional type like eigenmatrix. My users will be able to pass an eigenmatrix to this function. But what if they have a boost-Dublas matrix, or a Petsy matrix, or a Blaze matrix, or a Cutlass tensor, or a multidimensional array passed from Fortran? That's where Mdspan comes in. By using it in your interfaces, your code can work with any multidimensional data structure. Because Mdspan is just a non-owning handle, you can construct one that refers to an eigenmatrix, a boost-Dublas matrix, a Petsy matrix, a Blaze matrix, a Cutlass tensor, an array from Fortran, a built-in C array, or whatever. For example, suppose we had our own row major matrix class. We can add a simple Mdspan conversion operator, allowing us to pass our matrix class to any interfaces that expect an Mdspan. In some more complex cases, we might have to write our own layout type. Now, let's look at how we can use Mdspan. This is a simple 3D 7-point stencil inner kernel, similar to what you see in a proxy application like Minighost. We have 2 3D Mdspans representing the problem state. Using the Cartesian product of IOTA's technique I showed earlier, We build a range indicating the index space and then use a parallel for each to iterate that space. If we want to change the layout, all we have to do is change the input Mdspans. Everything else remains the same. Earlier, I showed you this example of a simple parallel matrix transpose. We used Mdspan and dealt with multidimensional indexing manually. That's not particularly portable. We've hard-coded a specific data layout which may not make sense in all circumstances. It's also error-prone, as it's easy to make a mistake in the indexing formula. We can improve this by using Mdspan instead. Now we can change layout by simply changing the type of Mdspan that we use. Mdspan has a powerful slicing interface, Submdspan. It takes an Mdspan and returns a sliced Mdspan. Submdspan is particularly useful for tiling operations, where you want to iterate over a small section of a matrix as if it were its own matrix. Because Mdspan is non-owning and cheap to copy, slicing is also cheap. You're just creating a new view of the same underlying data. The input Mdspan is not modified. For each extent of the Mdspan, you pass a slice specifier to Submdspan. There are 3 kinds of slice specifiers. You can specify a single index to be selected for an extent by passing an integral as a slice specifier. The rank of the returned Mdspan is reduced by 1 for each single index slice specifier. You can also pass a range of continuous interfaces to be selected for an element. Finally, you can pass a full extent to select an entire extent. For example, here we have a 3D Mdspan, M0, and we make a slice of it by selecting 8 indices from each extent, starting at indices 15, 31, and 7, respectively. The Mdspan returned by Submdspan, M1, will have a rank of 3. We didn't use any single index slice specifiers, which would cause a rank reduction. Each of the extents of M1 will be 8. Multidimensional indices for M1 will be offset by from what they would be for M0. For example, M1000 would be equal to M0 1531 7. Let's look at another example, this time with rank reduction. We'll slice M0, selecting index 15 for the first extent, the entire second extent, and index 31 for the third extent. The Mdspan we produce, M2, will have a rank 1. And the extent of that rank will be 128, the extent of the second dimension of M0. Iterating this 1D slice will be equivalent to accessing M0 with a fixed index for the first and third element. The set of standard C++ algorithms we have today is great, but not complete. What we have is primarily focused on manipulating one-dimensional sequences of objects. We only have a very limited set of numerical algorithms such as reductions and scans. We don't want C++ programmers writing their own versions of common numerical algorithms. We want them to use standard interfaces that are backed by an implementation designed and optimized for the platform they are running on. So the C++ committee is exploring new families of algorithms to standardize, starting with linear algebra. The C++ committee doesn't want to reinvent numerical linear algebra. We like to standardize existing practice. And the existing practice for linear algebra is BLAS, the Basic Linear Algebra Subprograms, which is a many decades old library originally developed in Fortran. But using BLAS libraries today from C++ is painful. They have low-level C interfaces, which often have a great number of parameters that describe things like extents, scaling factors, whether or not to transpose the inputs, etc. Good luck getting that function call correct on the first try, or understanding what it does when you come back to this code a year later. Depending on the platform, you may also have to deal with things like setting up library handles, transferring memory, etc. We want to standardize a modern C++ interface that can be implemented under the hood by existing BLAS libraries. Here's that same code written using the new C++ standard library linear algebra algorithms. The existing one-dimensional C++ algorithms parameterized data with iterators, and since C++20 ranges. For standard C++ linear algebra algorithms, we plan to parameterize data with Mdspans instead. We use the Mdspan parameters to express things that appear as distinct parameters in traditional C-style BLAS interfaces. For example, instead of having scaling parameters on matrix vector product, we have a scaled operation that takes a scaling factor and an Mdspan and returns a new Mdspan that will apply the scaling factor upon access. C++ standard library implementations can see through this abstraction and extract the scaling factor to feed it to a lower level BLAS interface that expects it. Another example is transposed, which returns a transposed version of the supplied Mdspan. As with today's C++ algorithms, we're planning to have serial and fork-joined parallel overloads of linear algebra algorithms. In this example, where we solve a system via upper triangular Cholesky factorization, we'd want to chain the two operations together and launch them asynchronously. In the future, we imagine we'll have asynchronous sender adapter forms of these algorithms that will allow you to do that. I have thrown a lot of information at you over the last hour, too much to be easily absorbed. So that you can come away from this with something useful, here are some of the important highlights. The C++17 parallel algorithms are a good-sized collection of fork-joined synchronous algorithms. They use exception policies to indicate which algorithm calls should be parallelized, but give the user no control over how or where the parallelism happens. The inputs to the algorithms are one-dimensional sequences indicated by pairs of iterators. C++20 ranges, especially the standard views that are part of the ranges ecosystem, make it easier to compose the inputs for the parallel algorithms and other traditional algorithms. Senders, schedulers, and senders algorithms provide composable building blocks for lazy asynchronous task graphs. Users have much more control over when and where the code runs. Senders just missed C++23, so they will almost definitely make it into C++26 in their current form. Mdspan is a non-owning multidimensional view of data. It keeps the common cases simple to use while providing flexibility, control, and extensibility over the rank, extents, layout, and access of the data. Mdspan is in C++23. Submdspan, however, will likely miss C++23 and be in C++26. The linear algebra proposal is an easy-to-use C++ interface on top of BLAS, using Mdspan as inputs. It is currently synchronous using the same exception policies as parallel algorithms. The proposal is still under active development. If all goes well, it'll be in C++26, though C++29 is also possible. All of the features listed here are currently available in the NVIDIA HPC SDK, which can be downloaded for free from nvidia.com. Senders, Mdspan, and linear algebra are experimental prototypes, in some cases very experimental. But all of them can be compiled for multi-core CPUs and for NVIDIA GPUs, turning the C++ committee's visions for parallel C++ into reality. There's plenty of other work to do down the road for C++ standard parallelism. Other classes of numerical algorithms, asynchronous streams, memory model extensions, affinity and locality facilities. But with every standard revision, we deliver more and more components of C++'s story for parallelism. I want to end where we started, with our goal. We need on-ramps to parallelism in standard C++. Almost all modern platforms are parallel, yet a shocking amount of code does not take advantage of that parallelism. So we want to normalize parallelism and accelerated computing. Writing parallel C++ code should be easy and natural. Parallelism should be the default. Thank you all for coming here and listening. Questions, comments, criticisms, thoughts, right?
Thank you so much. It was a lot of information. In terms of when and where, there was this example with inclusive scan, and I can understand about when it's set up through these adapters, I guess. But how about where? How do we set up schedulers there? Maybe I'm just behind it. Can you please explain it?
Okay, the inclusive scan example was setting up, right, a chain of senders.
Yeah, for example, if you want a GPU.
But it set it up as a sender that wasn't attached to any scheduler yet. So the result of calling that code is a sender, which then you can attach to a scheduler. You can get a sender from a scheduler and attach this one for the inclusive scan right after it, and so that it'll run on the execution context of that scheduler. That wasn't shown in the example. The example was just setting up the task graph. You can then use that in the way you use any other sender to run it whenever you want or wherever you want.
So inclusive scanning is in the end one big sender that was got from all these senders, and then it's passed to schedule. Yeah, okay, thank you.
Yes. There was one.
Yeah, thanks for the talk. A question regarding schedulers. You said there are multi-schedulers that can schedule to different computation platforms. Will it be possible to have like runtime decision for optional or priorities? So for example, I want to compute FFTs, but I don't know if the client platform will have a GPU driver available. And if not, please do it on the CPU, but if it's available, run it on the GPU instead. Yes,
you can write you can put whatever you want into a scheduler, into a want. So that exact thing of runtime checking, what hardware resources do I have available, which one's the best for this particular kind of problem. Yeah, people have been asking for that for years. I'm sure that will be a common scheduler once we get this out there in the wild. So yeah, that is a use case we will definitely support.